Welcome to Mission Control Focus Learners. I'm your flight director for today, and you have just secured an exclusive, highly classified look straight into the examiner's mind. Our target orbit for this mission, Cambridge, AS and A-level mathematics. Specifically, we're locking onto Syllabus 9709, Section 1.3, Coordinate Geometry, solving problems involving lines and circles. Now listen closely, because this topic isn't just some minor blip on the radar. It appears in every single examination series. I repeat, every single one. If you are aiming to push your propulsion meters and hit those top-tier A-star marking bands, you literally cannot leave this to chance. We are treating this explanation as a high-stakes flight simulation where there is absolutely zero margin for error. Buckle up. Let's initiate the launch sequence.
Okay, before we fire the main boosters, I need you to answer this critical, high-stakes question. What do you think is the single biggest mistake candidates make in coordinate geometry? Think about it. Is it forgetting the standard equation of a circle? Maybe it's messing up the quadratic formula when you're trying to find points of intersection? No, actually, scratch that. It's much deeper. It's a complete systemic failure in understanding what the examiner is actually commanding you to do. You see, way too many students treat coordinate geometry like a disjointed, random list of formulas. They're just plugging fuel into the wrong tanks. They plug numbers into equations without visualizing the actual spatial layout of the lines, the circles, and the strict boundaries that are operating within. Flying blind like this, it's a hidden expectation that costs thousands of students their top marks every single year.
And you don't just have to take my word for it. Look at this telemetry data straight from the official Cambridge Principal Examiner reports. Quote, candidates referencing cross-topic connections achieve significantly higher marks. So what does this actually mean for your flight path? It means top marks demand a connected, deeply conceptual understanding. You can't just know how to find a perpendicular bisector in total isolation. No way! You need to instantly recognize how that perpendicular bisector relates to the chord of a circle, how that exact chord is the key to finding the circle's center, and how that center connects right back to the radius. It's a massive interconnected web of data. Superficial breadth, just rote memorizing formulas, simply won't clear the atmosphere. You need deep structural knowledge to reach orbit.
Section 1. Core Theoretical Principles. Let's calibrate the launch track. Let's look at the core navigation system of the Cambridge assessment, the method marks strategy. Now, I really want to reassure you here, so take a breath. Cambridge examiners are not just staring at your final destination coordinates, they are actively evaluating your entire analytical flight path. Earning assessment marks is heavily based on demonstrating the absolute correct mathematical procedure. They want to see your logical, structured reasoning, regardless of whether a tiny arithmetic error throws off your final answer. If you set up the simultaneous equations perfectly to find where a line intersects a circle, and you substitute correctly to form your quadratic equation, boom! You are banking solid method marks. Your analytical process is completely sound. A simple addition error at the very end won't abort the entire mission, but only, and I mean only, if your method mark strategy is explicitly written out on the console for the examiner to see.
So, to max out those method marks, we need to completely understand the theoretical architecture of 9709. Top-performing pilots build their responses using 4 unshakable pillars. First up, precise definitions. You need to know exactly what a tangent is, what a normal is, and how their gradients relate mathematically, that negative reciprocal relationship. Second, causal relationships. Understanding that simply because a line is a tangent to a circle, the radius to that exact point of contact is caused to be perfectly perpendicular. Or knowing that the discriminant of their intersection equation is going to be exactly 0. Third, systematic analysis. This means taking a massive complex word problem and calmly breaking it down into algebraic steps without triggering a panic alarm. And finally, the fourth pillar, evidence-based reasoning. Show your work. The examiner literally cannot give you marks for mental math. If your telemetry isn't printed on the page, it cannot be graded. This framework is exactly how elite candidates seamlessly transfer their knowledge to entirely unfamiliar exam parameters.
Section 2. The procedural framework. Let's move into execution.
All right, let's walk step by step through the ultimate examination sequence to lock in those crucial method marks before time runs out. Step 1. Deconstruct the question. What is the actual command word here? Are they asking you to find, show that, or hence? Step 2. Extract the relevant data. Pull those coordinates, the circle equations, the gradients right out of the text and list them on your dashboard. Step 3. Select your analytical framework. Are we deploying the distance formula today, the midpoint formula? Are we completing the square to find the center of a circle? Step 4. Execute with crystal clear notation. Don't just dump a jumble of numbers onto the page. Label your equations. Write out, substitute equation 1 into equation 2. Tell them what you're doing.
And step 5, present with correct terminology. Always conclude your proof by stating exactly what you just found. If you skip this 5-step sequence, honestly, you are flying without a navigation system.
And speaking of that navigation system, your data interpretation has to be meticulously presented to secure maximum points. This means strict, unwavering adherence to proper headings, correct terminology, appropriate formats, and clear annotation. When you are finding the equation of a tangent, literally label it equation of tangent. When you find the center of the circle, label it center C. When the examiner is scanning your paper, it should read like a perfectly optimized flight log from top to bottom. Messy notation is just static on the radar, and it causes the examiner to completely miss your brilliance.
Section 3, Top 3 Examiner Warnings. Pay close attention, these are critical alerts.
Launch trajectory hold. Before we deploy our next sequence, we need to talk about system failures. Here are 3 major traps that past students consistently fall into, pulled straight from the principal examiner reports. Trap number 1, confusing cause and effect. A candidate might assume a line is a tangent before they ever actually prove the discriminant is 0. And they use that wild assumption as their starting point. Guys, you cannot use the destination to justify the journey. Second trap, forgetting to check format and presentation. You might calculate the correct radius and center. Awesome. But then, when asked for the equation of the circle, you just leave it as an unsimplified messy string of algebra instead of the standard format the question specifically requested. Total unforced error. Third trap, providing generic answers instead of plugging in the specific coordinates. A student might look at a problem involving a specific circle modeling a radar zone and just write out textbook definitions of a circle without ever inserting the actual coordinates of the radar station given in the question.
Let's actually put this on the main monitor and compare. A generic response versus a context-specific, high-level response. A generic answer just says, to find the intersection of a line and a circle, use simultaneous equations and the quadratic formula. Well, guess what? That earns 0 marks. It's empty fuel. Now, a context-specific, top-tier pathway actually performs the operation, explicitly linking every single data point to the scenario. It says, substituting the linear equation y equals 2x plus 3 into the circle equation x squared plus y squared equals 25, we derive the specific quadratic. Do you see the difference there? The examiner wants to see you execute the mathematics on the actual payload, not just read the flight manual back to them.
Section 4, Advanced Critical Analysis, pushing into the upper atmosphere. Okay, when you reach the higher-order assessment objectives in these A-level 9709 papers, you aren't just being asked to calculate, you must evaluate alternatives and provide heavily justified recommendations. When asked to prove a complex mathematical relationship, say explaining why 2 different circles might intersect twice, touch once, or never intersect at all, you must execute a flawless comparative analysis. Look at this matrix. You must identify similarities and differences clearly. You must use comparative connectives to logically link your geometric ideas. You must support each comparison with hard, undeniable numerical evidence calculated directly from the coordinates, like comparing the exact distance between centers to the sum of the radii. And finally, you must draw a definitive conclusion. If you just list the distances without actually comparing them to the radii, your structural logic drops, and your score completely plummets.
So essentially, there are 3 assessment altitudes you need to scale: descriptive, analytical, and evaluative. A descriptive student is flying at low altitude. They just write down the formula for the length of a line segment. An analytical student climbs higher and correctly calculates that specific length. But the evaluative student, the A-star candidate clearing orbit, they actively question assumptions. They look at the coordinate plane, realize there are 2 possible solutions for a point that is a certain distance away from a line, and they evaluate both mathematical perspectives. Then they actively discard the one that falls outside the domain given in the question's constraints. That right there is exactly how you reach the maximum evaluative marking levels.
Section 5, Final Exam Strategy Checklist. Time for the final system review.
To ensure you never, ever blank out during the actual exam, we're uploading a critical memory hack to your dashboard right now. Create a custom mnemonic using the first letters of key terms to quickly recall your procedural steps. For coordinate geometry, I want you to think of the acronym CLEAR. C stands for coordinates extracted. L is for lines and their gradients identified. E means equations formulated. A is algebraic substitution executed. And R, review the final format. CLEAR. This straightforward flight-tested mnemonic will absolutely help you recall your procedural steps and complex definitions when the exam pressure hits and your heart rate starts to spike.
All right, the tools to conquer these papers are officially in your hands. But the mission doesn't stop here. The real test begins when you sit down in that exam hall. So here's my final question to you. How are you going to adapt your study routine today to ensure you aren't flying blind tomorrow? Start applying the CLER framework to your past paper questions immediately. And hey, before you log off, take a second right now to subscribe to Ace the Exams, and make sure you hit that notification bell so you never miss our weekly flight-tested exam hacks. Drop a comment below letting us know exactly which Cambridge level, IGCSE, O, AS, or A level you are preparing to conquer next. We'll see you in the next explainer. Mission accomplished.